Alithia, and welcome everybody. So very pleased to be introducing this first webinar of the SusFE project. So the SusFE project is supported by the European Commission's Horizon Europe program. And today we're going to be talking about the EU's legislative framework for sustainable, eco-friendly electronics. We've got three great speakers today, and they're going to give short presentations, and then there'll be an opportunity for questions and answers. You can put those into the question and answer facility or either in the chat. So we can start off by Dr. Yves Bayon, who's a chief scientist at Sofradim production, which is part of Medtronic. So over to you, Yves.
Thank you. So good afternoon, good morning, so wherever you are. Alicia, could you share the slide of my presentation?
Yes, we will do so. 1 second.
Thank you so much. So the topic of today is sustainability. Sustainability is, I would say, a more and more important topic for electronics and also for medical electronics devices. So we may speak about exemption, limitation, and so on of the calendar. But I will show some data. Next slide, please. And just to say that our waste is, I would say, a real challenge. Healthcare accounts for 5% of global emission. Of course, not all of this emission and waste are coming from electronic. You have a picture, on the right showing some examples of waste. But this is becoming more and more a critical issue. And now many medical technology companies are committed to net zero policies with implementation sooner or later, with some agenda well defined, and also for most of the corporate companies in the ESG annual report. And this strategy, whatever the size of the company, should be implemented, elaborated, should be designed at the enterprise level. So every function, every people should be engaged. As underlined so far, waste is a major challenge, with more than 3.5 kilograms of waste per hospital bed per day in high-income countries. And the operating room where surgery are done is a major source of CO2 emission, because main products are single-use, and recycling and reprocessing is not so done currently. And as well, what's going on is, we speak more and more about it, the digitalization of patient pathways and operational excellence, and along, the full pathway from the raw materials, from the supply chain, and the end of life of products. Also, to balance the sustainability challenge, this is coming with after COVID, after the implementation for medical technologies of the medical device regulation, also with some supply chain issues the last 2-3 years. So that means there's one more challenge, and they can all be embraced, right away and with direct implementation. We should start, but there will be a long-term project, and we should be patient as consumers, as patient, and as part stakeholders of the FTech industry. Next slide, please. And this response to the environmental challenges comes in 4 pillars. First, to address the materials of concern in products, like, you know, the hearths in electronics in terms of recycling, in terms of reuse. Also, some products have some inherent toxicities, you know, maybe their use should be limited. And also the packaging. Packaging generates a lot of visible waste. To address the data availability, quality, and management to secure an environmental policy, the sustainability value proposition towards, for example, healthcare providers when they are the users of our electronics products, and also to put in place a governance and to manage the knowledge. Next click, please. And this should come to the implementation of a full ecosystem to create sustainable value with all end users and stakeholders. Next slide, please. Just to give you an idea, more focusing on electrical and electronic equipment. Electronics, all industries, all products aggregated, consolidated, the amount of materials put on the market is increasing with the years. The materials collected, treated, recovered, or reused or recycled increase in the same way, but we are still at about 1/3 of the electronic and electrical equipment put on the market, reuse and recycle. The trend has not been inverse, and expectations are there. Next slide, please. Another way to express the waste of electrical and electronic equipment, and you see some figures of the kilograms per capita of waste for the major EU countries, and ranging between 6 to 16, with an average for the European Union at 10.5. So for each individual, so there's a lot of electronic waste, and more than 4.7 million tons of electronic waste, as published by a Eurostat in 2023. Next slide, please. In terms of distribution of this waste, it's not surprising that most half of the waste come from large household appliances, as figured there. And then you have other categories. And the last one, over, I don't know if you, is about, 7.2, and made of electrical tools and medical devices. Just about 7.2, but representing 7.2 of about 5 million tons of electrical and electronic component. If it is just 5%, it is already, I would say, a large number, with more than 25,000, even more. So I don't want to make a calculation, but it is about 250,000 tons of waste in Europe annually. Next slide, please. And then, so why should we need to recycle electronic and electrical waste? So the numbers are impressive. That's the first point. And also, why? Because discarded electronic and electrical component can contain some harmful chemicals that may then pollute the environment if sorting, collection, the reuse or reprocessing of this equipment is not done correctly. And we have so two restrictions. One, due to the hazardous nature of substances, and EU rules will restrict and start to restrict the use of such substances. And as well, so there is the impact, the social impact. And as you may know, rare minerals, rare earths are widely used in electronic and electrical equipment. And some of those minerals come from countries that do not respect human rights. And it is also for the European Union, European Community, to have some trade policies to help to promote the human rights and to not use those important raw materials at the expense of human rights. Next slide, please. So the first regulation directive is a waste from electrical and electronic component to guarantee sustainable production and also consumption. Then, so the first priority is to manage in a better way the waste of electrical and electronic component. Second point, to guarantee or to facilitate the efficient use of resources and the retrieval of raw materials through reuse, recycling, and other forms of recovery. Our resources are not eternal. Our resources are not unlimited. They are limited. So we have to think about the next generation. And improving the environmental performance of everyone involved in the life cycle of electrical and electronic equipment. So that means from the raw materials, the manufacturing processes, and then the end of life of the product. And possibly before the end of life, the reuse or the reprocessing of such equipments. And in order to achieve these objectives, the directive will require separate collection and proper treatment of electrical and electronic equipment waste, and to set some targets for their collection, as well for their recovery and recycling, to help European countries to guarantee the human rights. So that means to find illegal waste export from countries not applying properly human rights for the exploitation of minerals, and also to harmonize the way to manage waste of electrical and electronic component at the national level, and to have less disparity of management policies from one country to another one of the European community. Next slide, please. Batteries. Batteries is also a very important topic, and the revised regulation entering in force in August this year, and replacing the first one from 2006, just to ensure as well, so the same trend, the same, I would say, needs to guarantee that batteries placed on the EU market are sustainable and can be sustainable throughout their whole life cycle. Once again, from the raw materials sourcing, manufacturing processes, sorting, collection of batteries, recycling, reuse, reprocessing, and so on. So this is very important, and notably this directive will give some direction to allow the replacement of batteries to prolong, to extend the life of electrical and electronic components which are still in use, which can still deliver the intended function, but with the replacement of the battery, and also to guarantee that the battery can be more easily removed from the device. That's the kind of things to be put in place in the coming years. Next slide, please. Also, the JRC has released a framework, the Safe and Sustainable by Design, to assist any parties, public, private, for the development of new products. And this from the very early stage. Next slide, please. Next slide, please. Thank you. And Safe and Sustainable by Design principles, the short name, the nickname is SSbD. It is a collection of green engineering, green chemistry, sustainable chemistry, some tools like the life cycle assessment to assess the true environmental impact of a process, of a raw material, and then to consolidate at a higher level, ultimately for the product itself. Should be safe by design. That means to select not harmful substances, or to limit the use of harmful substances according to the limits set by the new regulation, and to define the risk assessment, not only what we do generally from a manufacturing perspective or from a use perspective, but also from environmental, social, and governance perspective, and to define achievable, sustainable development goals from the beginning, and then to guarantee at the end a safe and sustainable by design of new electrical and electronic equipment. Next slide, please. And then, so the safe and sustainable by design SSbD framework is also based on the driver pressure step impact response framework. And with the 3 points as highlighted on this slide. And so first, to focus on resources and processing related aspect, for example, to reflect the type and quantity of resource input, and associated resource efficiency and circularity considerations, circularity meaning reuse, reprocessing, and so on. Pressure aspect on the environment, but not only on the human health, on society, for example, emission to water, soil, of air, which may, contaminate this environment for short term, long term, or forever. This should be particularly well documented, and this coming from raw materials. Impact aspects and the pressure aspect, once again, in all dimensions, is not only the environmental dimension, but the safety dimension, the social dimension, and economic dimension. Next slide, please. And there's a very snapshot, very high-level presentation of the safe and sustainable by design framework. But this can be initiated from the very beginning of any projects. And just for example, you can dig into the scientific and grey literature, EU legislation and guidelines, really accessible. And on this slide, so I have always included the web link of the information displayed on this slide, the certification schemes, documents from companies, notably the companies delivering from which we can purchase the raw materials, the chemicals, and also from NGOs delivering also some very useful information. Information on what? Safety, environmental dimension, safety and social dimension, safety and economic dimension, and so on. So on all the dimensions expected to run a safe and sustainable by design project. And this document should be reviewed and then should be a support for decision making. And whenever it is possible, then to make the right choice with the right balance between the safety, environmental, social, economic impacts, and what we expect to be delivered by the electrical and electronic equipment. Next slide, please. So there was a brief presentation that was just to be seen as an introduction. And you see these bottles in the fountain, and it is a treasure, so we should protect. And I don't want to see any bottles or this to be stored in such a old historic fountain. So that means that we should work together, and we should be collectively engaged at the individual, at the collective level. And wherever we are, so in an academic lab or in a company, it is our duty to work on sustainability to guarantee the life we experience today for the next generation. Thank you so much for your attention.
Thank you very much, Yves. If I may, we'll take the questions at the end, and very pleased and delighted to be introducing our next speaker, Dr. Maria Smolander, who is a research team leader and project manager on flexible sensors and devices at VTT in Finland. So over to you, Maria.
Hey, thank you so much, and nice to see you all online. Good afternoon. So I hope I'm sharing with you now my slides. Wait a second, I will put it to slides. So can you all see it? I hope. Let me know if not. But yeah, excellent presentation by Yves to start. So at least I don't need to justify that why we are working on that. But now I will briefly tell the VTT perspective to sustainable flexible electronics. So indeed, as we already heard, at the moment we are producing a lot of e-waste, and we are not recycling it sufficiently enough, and we are over-consuming some rare raw materials. So we need to work on that. And at VTT we have been taking also quite holistic approach on this aspect, the environmental sustainability naturally like one of the key elements, but also we are trying to take into account all the time the social and economical sustainability as well, and also trying to contribute to sustainable development in different phases of the life cycle of the product, from the design point to through materials and processes to use and disposal phase, and also we want to kind of like make wise and sustainable selections from all the way from materials to the system level as well. And if we think about the design phase, one approach what we have been taking is the modular design. So if we have modular products, that is facilitating the partial reuse and recycling of the electronic products. Also, we are looking at new ways to power the flexible electronic solutions. Like, for instance, we have been developing energy autonomous smart labels. Then in material side, we are trying to look at the renewable materials, abundant materials, and also developing tools for material traceability, for instance, through printed data carrier solutions. Then the processes focus in energy and resource efficient processes from our perspective, and printing is of course like a nice example, as it's an additive manufacturing method. So let's talk a little bit more about that in the forthcoming slides. And then in the usage and disposal phase, we are talking about aspects on like recyclability, reusability. Again, the modular design is of high importance. Product passports to monitor the history of the product and materials. Also considering the feasible waste streams and naturally also the social and economical sustainability from the use case point of view, like for instance developing solutions which have positive impact on health, as in this case, but also applications which can kind of improve the economical sustainability, for instance through a more efficient logistic chain as well. So they are options as well. And indeed, I already mentioned about printing, a very energy and material efficient manufacturing method as additive manufacturing method, and also sustainable in that sense that the flexible printed electronics, often the solutions can be rather lightweight. They can have reduced dimensions in comparison to state-of-art electronics, and also the manufacturing method is compatible with several renewable materials as substrates and as functional inks. And in this area, in a VTT coordinated ecotronics projects, our collaborators from Lund University compare traditional PCB manufacturing process with printing-based process, and actually they found out in the LCA study that the global warming potential was reduced down to 14% of the original when we changed the process from the traditional FR4 and etched copper-based process to a printing-based process with either PET or paper as substrates, and a silver nanoparticle ink as a conductive material. And in the traditional process, most of the environmental impact comes from the use of energy, but also a lot comes from the use of different chemicals in the etching process, and so still, if we think now about this remaining environmental impact, which is already a lot smaller than the original, but if we think that what kind of contributes this environmental impact, we saw that was mainly due to the use of silver ink, which is like the state-of-art material in printed electronics. And if we could even decrease the use of silver or make it more efficient, we could go even lower. And potential ways to combat this environmental load by silver would be, of course, more efficient recycling of the ink. But in a way, I think that's a little bit challenging still to achieve. But it's also good to look at alternative conductive materials whenever possible. So we have been thinking about copper and graphite. There is a lot of activity globally, for instance, with copper inks, which have some issues with the processing, and on the other hand, the carbon-based inks are not as highly conductive as the silver-based inks. But if it's possible, even to some extent, to decrease the use of silver, that is always great. But that's really an important way to decrease the environmental load. Then some words about the substrate. The template where you start building your electric device. That is also of importance in flexible electronics. Typically, like conventional polymers, fossil-based polymers are the state-of-art materials. PET, polyimide being like among the most common ones. Further options come from biopolymers, which have very similar properties to the conventional polymers, but they are not based on fossil-based raw materials. And then a further option are the cellulose-based materials, like true biopolymers, which even can be compostable. And in this area, especially if we think about cellulose-based materials, they have good properties. They can be low cost, flexible, even biodegradable or compostable, and also they are easily disposable also through other recycling routes, for instance, repulping. But on the other hand, at the moment, many of these materials are still pretty rough and too absorbing, and the barrier and optical properties, as well as the moisture sensitivity, kind of are creating some challenges. But we are working on those materials as well, even at VTT, to make them more suitable. So this is a huge area as well. But yeah, I actually wanted to also say that it doesn't always mean that if we go towards more sustainable substrate materials that we are compromising in the performance. So this is, for instance, an example where PET, conventionally used polymer, was changed to cellulose acetate propionate as a substrate for silver-based printed conductors. And what could be seen was that the conductivity was actually improved. So we anticipated that this was because there was better adhesion between the printed silver and this bio-based substrate. So very encouraging observation here. Yeah, this is an example of a EGC patch built on nanocellulose. My colleagues have been working on this field, and here an EGC patch has been realized in 2 different versions. So in the upper one, all the electronic components and the printed circuits and the electrodes have been integrated on same nanocellulose-based patch, and this, of course, because of the full biodegradability and compostability of the substrate, open up new possibilities for instance, component disintegration at the end of the shelf life of the device. Whereas this other version is like based on the modular design, and here we have a reusable electronic module combined with single-use, fully like biomaterial-based and carbon-based electrode, single-use electrode patch. And in this case, of course, the reusability of the electronics is a benefit, and easy disposal of this electrode part of the device. So there are indeed different options, and that's an example of that. Then really quick examples of what has been done regarding the powering and the batteries, or what is being done at VTT. So we are looking at bio-based raw materials, for instance, using biocarbon instead of the graphite. Then we are also looking at processing methods which consume less energy through the use of less or not at all solvent, which always needs to be evaporated. Then also we are looking at possibilities to increase battery lifetime, which would be very sustainable from the raw material point of view, and also we are looking at solid state batteries to increase safety and also the energy density as well. So different topics in that area as well. Then one example of a smart label where we have built like an energy autonomous temperature measuring label for packaging, for instance, for packaging applications. And here the idea is this is indeed doesn't need a battery because it includes the inbuilt solar cell OPV and the supercapacitor, so it's basically harvesting energy from the indoor light. And here the idea is indeed that with the use of this label we are able to make the logistic chain more efficient and avoid product loss in the transportation of heat sensitive goods here, and we decrease the loss of material valuable goods in the transportation. And this has been also manufactured using the printing based manufacturing methods. Yeah, so please keep this example in mind, because that will come a little bit later still in the presentation. But before going to this evaluation tool, I still would like to say a couple of words about the end-of-life consideration. So always, indeed, the reuse of materials would be preferred, but all in all, the separation techniques have a very essential role. So we are working, and we still need to work more on the methods for material and component disintegration, and from the beginning try to design the products in such a way that this is possible. And also what we are working with is the tools to identify the reusable and recyclable materials and components. And if we think about that, what are then the waste streams? Because one of the tricky things is to collect the waste, and if we think about some flexible electronic solutions, they are not necessarily considered like electronic waste, but if they are a part of the mixed waste stream, then in principle the substrates can be oxidized for energy generation, and the metals recovered from the ashes. In plastic waste, the strategies can include the washing, electronic separation by washing before extrusion, and sometimes, especially if there is a risk of the kind of that the product is ending up to the nature, then the biodegradation is something which might be beneficial. But then at the end, as we have now noticed that this is actually pretty complicated thing, the sustainability of electronics. So there are several aspects which need to be taken into account. So for that purpose, we developed and published a tool called GreenTool, which is a qualitative tool for preliminary sustainability assessment in the design phase. And the idea is to have a concrete tool which you can use to benchmark different current and future products. And here we have formed 8 different sustainability criteria, and for each of them we have from 5 to 12 sub-criteria, and this can indeed be as a discussion or as a workshop, can be used to evaluate the possibilities to go towards more sustainable solutions. And we, for instance, implemented this to compare different smart labels, and that example is actually described in detail in this publication, which is mentioned here. And here we had indeed this energy autonomous label compared to currently used data lockers with coin cell batteries. And we anticipated different generations of this smart label and evaluated those or benchmarked those against the state-of-art technologies. And here, for instance, we could see that the biggest sustainability potential would be then in the raw materials and in the manufacturing. So there, the highest contribution to sustainability would come in these criteria. So finally, I would like to conclude and say that indeed the sustainable development requires a holistic approach approach, and luckily we have been really seeing that this problem is very widely at the moment tackled by several stakeholders, and definitely needs, as Yves was also saying, requires a lot of collaboration, and from the technical perspective we see that flexible electronics has a vast potential in this field as well, because of the nature of the operations and the wide possibilities in the material selections. But thank you so much.
Thank you very much, Maria. That was a great talk. Thank you. So our final speaker is Dr. Alexander Sergievs from BEFC in France. So Alexander, if you want to
yes,
share your presentation.
Can you see my screen?
We can.
Okay, perfect. So, as Yves already touched on it, so the batteries are quite a big problem for the electronics in general. And so, of course, we want to enable the data collection, such as for medical applications, for example. And there's also estimate that by 2030, we'll have about 30 billion devices connected to the internet, be it in medical or any other areas. And of course, the biggest problem is the power source, especially for environment, because the recyclability of them is complex, expensive, and for the most part unecological. In addition to this, about 97% of all miniature batteries, all chemistries, be it alkaline or lithium, end up in landfill, and about 1 in 3 adults in the surveys have admitted to just throwing them away in a general bin rather than a special one. And so to tackle this problem, so we have come up with kind of a more sustainable solution. What we have is a biofuel cell. It's based on paper and the enzymatic reactions, which are very similar to the ones that are happening in human bodies. The cell itself is organic, it's metal-free, it's disposable and recyclable, and in addition, it's thin and lightweight that can fit into patches, like for medical applications, as an example. It is sustainable, so it has about 100 times less CO2 emissions when compared to the production of a traditional coin cell battery. And then it's compostable. So here you can see the result of the compostability test of 45 days of industrial compostability trials. The fuel cell does not degrade fully because we have carbon parts inside, and of course all organics degrade eventually to carbon, and carbon itself is the lowest form of organic. The way it's made is basically a stack of paper layers, and then each paper has a different function. And then on the two sides, we have the different electrodes, and then one of them is having a reaction with the glucose and produces the electron flow. And then on the other side of the cell, we have a different enzyme that is reacting with oxygen and produces another electron flow. And then when we combine the two, we essentially have ourselves something like a battery. Because it's essentially a 2D shape, we can make it pretty much any shape and size to fit into whatever is required by the application. And then the power of the fuel cell depends on its area. So here you can just see a few examples of different fuel cells with different areas and hence different powers. We can also stack them in series if we need to increase the voltage. And we can, as I mentioned, increase the area to increase the power. In addition to this, what we also do is eco-friendly electronics. So here you can see kind of an example of a tag that can do various electronic that has various electronic components for different functionality. This particular tag is reusable, but we try to limit the amount of waste that goes into this. So, for example, the printed circuit board that it is on, it's 0.18 millimeter thick. So which is better than the standard 1.5 millimeter thick boards. This also can bend, i.e. it can go around an arm or something like that. We also validated different types of sensing that we can do with the power that is delivered by the fuel cell. So we can easily detect temperature and humidity. We can also do shock and angle sensing, as well as light sensing, either as just binary sensor, is there light or is there not, or to characterize how much lumens are hitting the sensor. We are now also working on the sensors for biomarkers, for pH and O2. And then we also can do some of the communication protocols. We can use either displays or standard technologies like NFC, RFID, Bluetooth, or even some gigahertz for long-range data transmission, such as Sigfox or LoRaWAN, or something like NB-IoT. Markets. So the markets that we see this fitting quite well would be something like Industry 4.0, of course, wearable health sensors, consumer goods, and of course there are other markets that we can target with this. The business model. So the scaling. This is although I showed you a stack of paper layers. This is a legacy technology, and what we are working now is to do the same thing but printed. So instead of having individual paper layers, we would we'll formulate the inks that have the same properties and then print them on a piece of paper. Afterwards, we just fold it and we have ourselves a working fuel cell. Because this process is roll-to-roll compatible, we can print these at high volumes. And then so we need the two processes, the printing and then the cutting, to then cut the final devices out of the big roll. We'll also do the printed electronics because this is what we are working towards. Similar kind of to what VDT are working on, and then we can provide the full solution if needed. So, and this kind of shows the vision for the final solution that we have. We are working with different partners such as 3M for adhesives, specifically medical grade adhesives, Avery Dennison for papers, ST for electronics, Pragmatic for some flexible electronics. And then what we envisage, basically having this tag printed on a piece of paper with the absolute minimum amount of electronics required to perform whatever function that tag was made for. And then a printed fuel cell essentially just printed here. And then that would be the full solution that you can throw away. And the only waste you would have from it would be silicon from the electronics, which itself is not that polluting, or at least it's not poisonous to the environment because it's inert. Awards and labels, this is just to say that we have a few just to say that it has been kind of validated by others, the technology that we have. And yeah, so we are kind of a startup. We did raise our Series A. There are about 45 of us working on all of this, and yeah, that is about it. Thank you very much for listening.
Thank you very much, Alexander. So we've had a great series of talks, starting off with Yves talking about the broader legislative frameworks, the safe and sustainable by design, and then a really nice talk from Maria in terms of applications around that for flexible electronics, and then a specific example around bioenzymatic fuel cells from BEFC. So we've got time for a small number of questions to our panelists, if there are any.
Hello, Sof. Not for the moment. We have not received any questions.
Okay, well, perhaps if I can just ask us, in general terms, Maria, you talked about this concept that you're developing for medical devices around having a reusable part and a disposable element. in the context of medical devices, how sort of amenable are the clinicians to this concept of, having reusable parts in a medical device? Is that a challenge, or do you think people are accepting of that?
Sorry, I'm muted. Yes, very good question. Yes, maybe Yves would be better to answer that. But yeah, you're right. I think that depends also a little bit on the market. But according to my understandings, in some areas, like everything is really like single use, and then going for kind of for hygienic reasons, and whereas in other countries there might be more partial recycling. But yeah, I agree that it's a little bit tricky. I don't really have a answer on that that indeed.
Okay, great. Thank
good,
you.
Very good point.
Well, I think, sort of, I guess, within health, it's generally conservative, but there is a need to move towards that. I was also very interested in your point around replacement of silver with copper and carbon, which I think is really great. And it's nice to see that you showed some examples where there could be some benefits even of that technology.
Yeah, and hey, by the way, one thing related to the previous thing, that of course it can also be something what like one person is like having in the personal use, and then it's a benefit that you can kind of implement like long-term use. Okay. So that's a slightly different use case, of course. Yeah.
Thank you, Maria. There's a couple of questions for you, Alexander. One which is a specific question around the current producing capacity of the fuel cells per square centimeter. And then also a second question, if I can give you that, is the approximate shelf life.
Okay. So thank you. So for the current generating capacity, it's about 11 milliamp hours per square centimeter. However, that is continuous. If we want to extract more, so it's possible in short bursts of maybe order of 50 milliseconds. It can support, I would say, up to 100 milliamps, but in a very short burst. In terms of the shelf life, so because it is made out of paper, it's very hard to do the accelerated tests, because the moment we start doing the standard accelerated testing, it just degrades immediately. So we have kept some fuel cells real time for 2 years now. And so far we have lost about 4% of their capacity over the 2-year period. So once the fuel cell can basically stay for 2 years before usage and just lose a little bit.
Okay, great. Well, thank you very much, Alexander. Can't see any other questions, but if I can ask Yves around the safe and sustainable by design approach, where are we, sort of in that? I'm relatively new to that, Yves. So if you could just tell me how you see that being implemented.
So yeah, I will speak in my own name as an employee of Medtronic, but not in the name of Medtronic. So I would say the safe and sustainable by design framework has already been used. Use cases have been reported, and to show the real benefit, and they all show the real benefit of this framework to generate more sustainable and safer products, and with a step-by-step approach. And I said, and I repeat, I insist on this for SusFE people, but for all the people joining us, this can be applied from the very beginning. And you have already information from academic literature, from scientific literature, from the manufacturers. All of this can be educated, and Maria has mentioned more or less on this point. So you can compare, you know, the raw material by themselves. You can compare, you know, also the sustainability performance from one provider to another one. You have more and more, you know, communication starting. Honestly speaking, and from my experience, it's still hard to get, you know, this information from all providers, or to have in-depth, you know, information from all providers. But this is changing because more and more parties will run life cycle assessment, and not life cycle assessment for one step, but more and more for the global impact of one product, starting from the raw materials, from any component which are sourced externally, and also the real impact of the manufacturing processes. And to comment further to what Maria has said, so to have a device, an equipment for which, you know, part is reusable, another one is disposable, I would say that's great, as long as we can separate easily, intuitively, the part to be recycled and then to be effectively collected. I would say yes. And once again, speaking in my own name, that's what, you know, I encourage anyone to do. And for the next generation of the devices, or for what, you know, emerging from the labs today, that's what we should consider, because the products will come onto the market in 3-5 years for the earliest of them, and later on for, you know, the most complex products. So that means this will be more and more expected, and anything you can do there can also generate not only a better impact from a social perspective, from a safety perspective, from an environment perspective, but also from a market perspective, because you will be where the users, the consumers, all the stakeholders are expecting to see the society to be. So yes, and to try the copper ink, and even it is not, I would say, as conductive as silver, but for some cases, it may be a good answer. And we don't need all the time silver. Copper may be just sufficient for some indication we have. And for the battery of BFC, okay, so we cannot, you know, power a car. That's true. So I'm just exaggerating, but to power some demonstrators, some products with temperature sensors, moisture sensors, or for LED screen and displaying some information, and compatible, as Alexander said, with many wireless transmission means, I would say the BFC battery is what you can use in a safer way. So that means we should try alternative solution. And maybe some of them are not as good as the one we traditionally use, but maybe just enough and sufficient for many, many applications.
That's great. Well, thank you very much, Yves. My thanks also to Maria and Alexander's. It's been a fantastic series of talks and some nice questions as well. So I have some final thanks to colleagues at Medtronic who've been in the background facilitating this webinar. And my thanks to you all for joining us today, and we hope to have a number of these webinars expanding on these discussions. So thank you very much and goodbye.
Thank you so much. Bye-bye. Enjoy your day.
Bye-bye.
Thank you very much. Bye.